Hey class, we're going to cover section 5.1 in your book today. So 5.1, before you start this section, there are a few things that you're going to need. So please, before you go any further in this lesson, make sure that you've got a protractor. Make sure that you have a note card or a ruler works, or your compass could also be helpful. So you might want to grab one of those. Also, you're going to need this sheet. Zoom out. This sheet right here. So this should have been an attachment in the one of the emails that you got from me. So look for that, print it out. If you don't have these things ready to go, pause this video and come back to it. If you have all of these things and you're ready, then let's start. So section 5.1, we're going to look at two specific types of segments inside of triangles. And then in 5.2, we'll look at the other two. So we're going to fill in these first two columns of this sheet together. All right, so first thing that I want you to do is in this top spot right here, let's move this down, the types of segments. This first segment that we're going to look at is a perpendicular bisector. So let's write that here. Perpendicular bisector. Now, a perpendicular bisector is going to bisect the sides of your triangle. Perpendicular bisector, it bisects the sides. And maybe you want to write that up here. Bisects the sides of your triangle. So we're going to draw this in. You could use your compass to do this. We did this earlier actually without you even knowing it with the compass when we were bisecting a side, creating a perpendicular bisector, right? When I just gave you one line and I said create a perpendicular bisector of that side and you used your compass. I can show you how we would do this. For some people, they think this is easier than going through and using the protractor. But you would put your put the point of your compass down and open this up a little bit more than halfway. You'd make one arc here, and you come on the other side and make another arc. Get my point there. And where those two arcs intersect, you would use a ruler, straight edge, something to that effect, and you would draw in your line right there. And that's a quick and easy way to do a perpendicular bisector. So if you like using your compass, absolutely go ahead and use that tool. For those of you who are just like, yeah, the compass wasn't my thing, then measure it. It's all right to do that for this section. Measure it, figure out where halfway is, make a mark. But we need this to be perpendicular. So again, you could take your protractor and you could measure 90 degrees. So I'm going to take a look at this. I'm going to put that mark right in the middle. I can make a point. Let's see. We're 90 degrees. Following this right here. Should be right up there. Okay. And I can draw in my line. The other way I can do it, let's say I don't have a ruler. This is why I said a note card works just fine, because a note card is going to have 90-degree corners, right? So if we can figure out where the midpoint is, where halfway is, then I can set my note card here in this corner, and I can use that. Any one of those three methods will help you get a perpendicular bisector, and you can see that that pretty much goes through where those two arcs intersected here and down here. All right, so it's perpendicular. I'm going to get a right angle. It's bisecting this bottom side, so I know that these two parts here will be congruent. Okay. So that's what I want you to do for that first box where it says drawings. I want you to draw in that perpendicular bisector. Don't freehand it. Practice measuring it. Again, you can use your compass, you can use your ruler, you can use your protractor to measure the 90 degrees, or you can use the note card. So you have a lot of different options. But what I don't want to see in your homework is I don't want to see you just guessing and just like throwing a crooked line in there. I want you to use a straight edge. I want you to be able to measure or construct where that midpoint should be, and to make sure that that's perpendicular. All right, I'm going to swap out my chart for a minute and bring in definition. So something else that you might want to have your notes separate from the chart that we're going to fill in. You might want to have your notebook or your binder, have a sheet of paper with you so that you can write in some extra things that were not going to fit in the chart. Perpendicular bisector, here's the definition of it. It's a segment that goes through the midpoint of a side and it's perpendicular to that side. Goes through the midpoint of that side and it's perpendicular to it. Some things that we will know: if this side is being bisected, we'll know it's cut in half. For example, let me label my triangle. If I label this A, B, C, and D, and let's say I know that AD is 3. So the distance from A to D is 3. Then I can figure out the distance from D to C should be the same, right? These are congruent, so this would also be 3. And the distance from A to C would be all of that together, right? 3 plus 3, so AC would be 6. So if I have a perpendicular bisector, I can figure something out about the side lengths. Now, you'll see in your chart, it says point of concurrency, right? So we're looking for point of concurrency. Point of concurrency means this is the point where 3 lines meet, all right? This is the point where we're going to draw in multiple lines. This is the point where those lines meet. It has a special name for perpendicular bisectors. We're going to fill in that special name right here. We're going to look at, is that point of concurrency on the inside, outside, or on the triangle? And then what kind of special relationships are there with that point of concurrency in that triangle? So I'm going to come back to this. All right, so we've got, see if I can fit all of that on there. All right, the circumcenter. Circumcenter, that's the point of concurrency. This is the name of the point of concurrency. Circumcenter, the common point of the perpendicular bisectors of a triangle. The circumcenter is equidistant from the vertices of the triangle. And the circumcenter can be inside, on, or outside of the triangle. All right, let me go over that again. You could copy this down for your notes. This is a good example to have. This is just the triangle, and for each of the sides, I've drawn in the perpendicular bisector. So I found the midpoint of each side and drew a line that was perpendicular. Found the midpoint of YZ, draw in a line that was perpendicular. Found the midpoint of XY, draw in a line that's perpendicular. This point right here is called the circumcenter. The circumcenter is where all the perpendicular bisectors intersect. It's where all of the perpendicular bisectors meet. All right, you need to associate these two together. That will be important in this chapter. Being able to match up perpendicular bisectors with circumcenter. You need to be able to match those words. Now, the special relationship, and I'll come back to the chart in just a minute and fill that out with you, but I want to explain the special relationship here. The special relationship is that the circumcenter is equidistant, that means the same distance, from the vertices of the triangle. Okay, so point C is the same distance, it's the same distance from C to Y, C to X, and C to Z. Now notice I don't have those lines drawn in. All right, sometimes in your book, they're going to put that in. They're going to put it in a dotted line. I'll show you what that looks like. This is the most common way that you will see this in your book. They will have a dotted line from that circumcenter to each of the vertices. And each of these dotted lines will be the same length. The green line is almost there, but not quite. So each of these dotted lines that I drew in, those represent the distance from the circumcenter to each of the vertices. And these dotted lines would all be the same length, the same distance. Okay, that's the special relationship. Now let me go back to the chart and I will help you fill out what we need to put in the chart here. All right, so we had perpendicular bisectors as this first column here. Had the perpendicular bisectors. I'm going to move that, come down here. The point of concurrency, fill this in on yours, is circumcenter. Circumcenter. And is that point of concurrency inside, on, or outside of the triangle? It can be any of those. Okay, the circumcenter can be inside, it can be on, and it can be outside of the triangle. Depends on what kind of a triangle you're dealing with. And the special relationship here, okay, that circumcenter is equidistant from each vertex. Equidistant from each vertex. Okay, so fill in your chart this way. Point of concurrency is a circumcenter. It can be inside, on, or outside of the triangle, and it is equidistant, same distance from each vertex. Okay, now we're going to come up to our second type of segment. We're going to work on the second column here, and we are going to talk about altitudes. Altitudes. For an altitude, the best thing to help you make your altitudes is a note card. Okay, that's the best thing to help you make your altitude is a note card. An altitude is a segment that goes from a vertex and is perpendicular to the opposite side or the line containing the opposite side. And I'll explain that last bit in just a minute here. So again, an altitude goes from a vertex and is perpendicular to the opposite side. So again, this is where my note card comes in handy because it helps me figure out perpendicular. So I can take my note card. I want the bottom of my note card to line up with the side of my triangle, and I'm going to keep moving it until I line it up with this vertex up above. Okay, once I hit that vertex and I see that it's lined up down here, I'm going to draw in that segment. Okay, that's my altitude right there. It goes from a vertex to the opposite side, and it's going to be perpendicular to that. Now I can do that from each side and each vertex. So I could do it from this vertex right here and line up my note card with that opposite side, right? And I could keep doing that, and I could draw that in, and I'd have another altitude. And same thing here. Okay, again, I want to line up that note card with that vertex and perpendicular to the other side, and I could draw that in, and I'd get all three altitudes in my triangle. I'm just going to draw one in for you so that you can see clearly what an altitude looks like and how it's different from a perpendicular bisector. You see that perpendicular bisector, it's not guaranteed to go to the vertex. It goes just straight up. Now, the altitude hits the vertex and it's perpendicular to the opposite side, but it's not necessarily bisecting this opposite side. So see the difference between these two? Okay. Now, one of the things that I said earlier was that an altitude is a segment from a vertex that's perpendicular to the opposite side or the line containing the opposite side. That part right there, or the line containing the opposite side. This can be a little bit tricky. Here's what I mean by this. This is why I have a second triangle here for you. Notice the second triangle is an obtuse triangle. First one was acute, second one, this is an obtuse triangle. This is where that whole line containing the opposite side comes in. Here's my vertex. If I want to draw an altitude, this is my other side. But my other side is here. And how do I get a line that's perpendicular from this vertex? Well, what I have to do is I have to extend this opposite side. So I'm going to extend this opposite side here. Okay, I've extended that opposite side. Now I can put in from this vertex a line that's perpendicular. Okay, again, I'm going to line up my note card, make sure it's nice and straight along the bottom, make sure that it lines up with my vertex up on top. Go straight down. That right there, that's my altitude. Okay, this is the altitude, this line here. Notice that the altitude is outside of the triangle. That's okay. An altitude can be outside of the triangle. Sometimes it'll be inside, like an acute triangle. Sometimes it'll be on the outside, like an obtuse triangle. And notice that I gave you one more triangle down here. The reason I gave you one more is a different type of triangle. Here you've got a right triangle. Well, what happens if I want to draw an altitude, let's say from here? I want to draw an altitude from this vertex. It's going to go to the opposite side, and it needs to be perpendicular to the opposite side, right? Well, if I take my note card, I've got my note card along the opposite side. I wait until I get it lined up with that vertex. And what happens? It turns out that the altitude is this side right here. Okay, this is the altitude in a right triangle. So once again, your altitude can be inside the triangle, it can be outside of the triangle, the altitude can even be a side of the triangle. All right, now let's take a look at a few things outside of the chart. I'll come back to the chart and help you fill that in just a minute. So you've seen me do this on the chart, but I just want to show you this again in case you wanted to write down this definition here in your notes. The altitude is a segment from a vertex that's perpendicular to the opposite side or to the line containing the opposite side. The altitude might be inside, on, or outside of a triangle. And again, you have these examples, but you have these examples also in your chart too of the altitude being on a triangle if it's a right triangle, or being outside of the triangle if it's an obtuse triangle. Okay, on your chart, then you also have below this the point of concurrency. And where does that point of concurrency lie, and what special relationships might we have? So here's what I want to show you. If I were to draw in on that acute triangle, if I were to draw in all three altitudes, my drawing would look something like this. All three altitudes drawn in. The orthocenter is the common point of the altitudes of a triangle. So this little point right here, point O here, that's the orthocenter. Orthocenter and altitudes, you'll need to associate those two. You'll need to remember that those two go together. The orthocenter, it's the common point of where all the altitudes meet in a triangle. The orthocenter can be inside, on, or outside of a triangle. So let's take that back to our chart. Remember, we've got orthocenter. Orthocenter can be inside, on, or outside of the triangle. So going back to our chart here, we're going to fill in this part underneath the triangles that we drew in. The point of concurrency with all of the altitudes is called the orthocenter. And the orthocenter can be inside, on, or outside of the triangle. And as far as the relationship goes, the special relationship with the point of concurrency, there isn't any kind of special relationship. All right, so we're going to leave that one blank. There's no kind of special relationship there. We get a freebie on that one. Okay, so 5.1, you're going to be seeing problems that have to do with the perpendicular bisector and the altitudes. Okay, again, perpendicular bisectors, you get all three of them in a triangle. Where all three of the perpendicular bisectors meet is called the circumcenter. That point, just that point, can be inside on or outside of the triangle, and that point will be the same distance from each vertex. With the altitudes, you can draw all three of the altitudes in. Altitudes themselves can be inside, outside, or on the triangle. Where all three altitudes in a single triangle meet is called the orthocenter. That point can be inside, on, or outside the triangle, and it doesn't have any special relationship with the triangle or vertices or anything like that. That's what your chart should look like. Now, one more thing that I want to cover with you, because they're not just going to leave it as simple as, hey, answer these questions that you filled in from your chart. They're going to give you some other types of problems, and you'll need to know how to do them. So I want to remind you, Pythagorean Theorem for right triangles. I'm going to zoom in here. Pythagorean Theorem for right triangles, and we will be dealing with right triangles. Remember, this is a squared plus b squared equals c squared. A and b are the legs, c is the hypotenuse. So if you know two of these, you can plug the numbers in for whichever two you know, and you can solve for the missing side. That's going to come in. We're going to use that in this section. Here's an example of something that you might see. This is a type of homework problem that you'll see. Now this might look confusing because you go, Mrs. Durr, when you just drew the perpendicular bisectors and the altitudes in, you drew them all the way through the triangle. And they're not drawn all the way through the triangle here. How do I know if I'm dealing with perpendicular bisectors or altitudes? Good question. Here's what you're going to look for. You know that you're going to have perpendicular lines, right? Because both the perpendicular bisector and the altitude had perpendicular lines. You know that they're going to be perpendicular, right? Okay. The other thing that we're going to look for is, are the sides of the triangle being bisected? The sides of the triangles, or the sides of the triangle, are marked as though they're being bisected. That tells me that I'm dealing with these black sides here are perpendicular bisectors. Okay, I'll say that again. These black sides right here, these are perpendicular bisectors. Man, my alarms like to go off every time I'm making a video. All right. They're perpendicular bisectors again because we see that they are perpendicular and because they are bisecting each of the sides of the triangle. So to fill in the answers for our questions here, it says that C is the what? We're looking for what's that point of concurrency called. So the point of concurrency for perpendicular bisectors is the circumcenter. And then they're going to ask us questions, and we got to fill these in, right? So if GC equals 14, GC right here, if this is 14, then what is CF? Well, the special relationship with the point of concurrency here with the circumcenter is that that circumcenter is going to be the same distance to each of the vertices of my triangle. So these red dotted lines you see here are all going to be the same length. So if GC is 14, then CF would also be 14. Okay, separate problem now. We're not carrying over. If EH is 15, then how long is EF? So if this right here is 15, how long is that whole side? Well, this is being bisected, right? So if half of it is 15, then the whole thing is going to be 30. And the last one we have here, if CF, this guy right here, if that's 17 and IF is 14, then what is, IF. So again, I'm going to start this over. If CF is 17, IF is 14, how big is CI? this is the right triangle. So if I bring this out here, I'm going to kind of straighten it out a little bit. All right, I've got C, I, and F. CF is 17. IF, maybe I should move this up so you can actually see what I'm doing here. All right, IF is 14. And we want to know what is CI over here. So we're going to use that Pythagorean theorem. Remember the idea of a squared plus b squared equals c squared. C is always your hypotenuse. This is always the longest side. That's your hypotenuse. So 17 squared equals, these are A and B. It doesn't matter which is which. Okay, let's say I'm looking for A and this is going to be B, 14 squared. Grab my calculator. I can plug these in. I've got A squared plus 14 squared is going to give me 196. 17 squared is going to give me 289. Move that 196 to the other side. Okay, subtract 196. And I'm going to get 93. Okay. So if I want to get A by itself, I'm going to take the square root of both sides. So A is going to be the square root of 93. Or if I put that in my calculator and I want to get a decimal, that's going to be approximately 9.6. So you one quick heads up, this is in the homework. So I wanted to tell you something about the homework problems. This is specifically 5.1. You'll see it in 5.2 also, but I'm going to show it to you right here in 5.1. These problems here, where they say copy each triangle and draw either the perpendicular bisector or the altitude from each vertex. A couple of things here. First of all, notice that they say from each vertex. All right, so not just one, don't just draw in one for each of those, but each vertex. But what I really wanted to address is the copy each triangle. Couple options here. So one thing that you can do is you can take your notebook paper and you can put it right over on top of this, and if you can see through your notebook paper well enough to trace these through, then go ahead and do that. If that's just not working for you, if your notebook paper is too thick or you can't accurately trace them, go ahead and take this sheet, put it on. If you've got a printer copier at home that'll allow you to scan this or make a copy of this page, you can copy it, print this page out, and then you can actually do the exercises on the printout itself and not have to worry about tracing the triangles or anything. But listen, what I'm looking for here is I'm looking for neatness. So if you're going to copy, if you're going to trace these onto your notebook paper, please make sure that you're using a straight edge, whether it be the side of a note card or a ruler, but make sure that these triangles are nice and straight. Don't freehand sloppy them looking like you're driving in the car while you were trying to copy your triangles onto your paper, right? Nice and straight, use a ruler or the side of a note card, something like that. And the same thing when you're actually constructing these, whether you use your compass or you use a ruler and protractor, note card, however you do it, make sure that the segments that you draw in are nice and straight, that I can easily tell if you're trying to bisect the whatever side of the triangle you're doing, and make sure that you do this for each of the sides of the triangle. Same thing down here. Make sure that you are accurately drawing in, neatly drawing in that altitude for each side of the triangle. And notice that you've got the obtuse triangles here too. So be careful about how you do that. And those points of concurrency may meet either on, inside, or outside of those triangles that you have there. So also I recommend doing it in pencil. So if you make a mistake, you can easily erase that without having to start all over on everything. Now the other thing I wanted to show you, it's just right over here on the next page. When you get to problems like these, do be careful here because sometimes it's kind of confusing. Well, what kind of segments are we dealing with? Go back and double check your segments if you're not sure. Notice that these segments here, they start at a vertex and they're perpendicular to the opposite side. Vertex, perpendicular to the opposite side. So they all follow that pattern here. So take a look back at the special segments to see What kind of segment always goes from a vertex and is perpendicular to the opposite side? Over here, notice this is one of those ones I was showing you. They don't actually draw in the entire segment. They're just drawing it to that point of concurrency. And then we've got those dotted lines here. So hopefully that should tell you what kind of segments you're dealing with in that triangle. When they're asking you these questions and they're saying, name all the illustrated perpendicular bisectors, don't take for granted that, oh, all of these and all of these, they're all perpendicular bisectors. No. All right. Some are, some aren't. So take a look at the triangles and take a look at, in each triangle, what kind of segments do you have? All right. So each triangle is going to have just one type of segments. They're not going to mix and match. Each triangle is only going to have one type of the special segments.